Okay, so we're going to talk about integers and rational numbers. So if we go through this, here are a few definitions for you to write down. So these are starting off with your whole numbers. That's like numbers you learned how to count with. Integers are numbers including negative signs, like positive and negative. Positive integers, obviously greater than 0. You can abbreviate. You don't have to write everything word for word. And negative integers would be less than 0. So whole numbers do not include negatives. So if somebody says, give me a whole number, negatives are not included in that. Okay. All right. So the next thing we're going to look at is right here. So rational numbers. And rational numbers are a number where A and B are integers and B cannot be 0. So you can't divide by 0 or have 0 in your denominator. This is a sort of a Venn diagram of what the numbers are included. So it's probably easiest if you draw the small circle first. So natural numbers don't include 0. Natural numbers are like when you first learned how to count. Like when I'm counting with my 3-year-old daughter, I don't start at 0. She has no concept of 0 yet. So I start at 1, right? And then usually you go up to 10. And once you learn that, you go up to 20. But you don't really say 0, 1, or at least most parents that I know don't do that. And then when you start learning about 0, probably in kindergarten, first grade maybe, I think kindergarten, that would be considered your whole numbers when you throw in 0. And then here's your integers. And then rational. So rational numbers, they can be fractions or decimals that are repeating or that terminate. So a repeating decimal, like 1/3, right? 0.33 repeating forever would be rational. Or a decimal that terminates, like half would be, if you made it a decimal, would be 0.5. That's it, 0.5, right? So that's terminating. So those would be examples of rational numbers. And then irrational numbers are numbers that don't terminate and they don't repeat. So for example, pi is 3.14 on and on to infinity, right? Because it doesn't ever repeat or terminate. If you type it into your calculator like square root of 3, you are going to get a bunch of random numbers in your calculator that don't terminate or repeat. So that should tell you that that's an irrational number. So if you understand how Venn diagrams work, you're looking at this, and this would tell you that a natural number would also be considered, I have this backwards, excuse me, a rational number. No, rational numbers would just be rational. Okay.
Natural numbers are all.
Yes, but a natural number, you could also call it a whole number. You could also call it an integer, and you could also call it a rational number. Okay, so same with integers. Integers can be integers, or you could also call them rational. And all of these numbers are real numbers. And yes, there is such a thing as not a real number. It's called an imaginary number. And you'll learn about that in Algebra 2. Yeah, so we don't learn about that in Algebra 1, but you will eventually learn about something called an imaginary number that's not a real number. So irrational numbers, the only other category they fit into would be real numbers. They can't be called integers or whole. Okay? Everybody good with that? Okay. All right, so what we're going to look at is determine what categories these fit into. So if you look at the number 5, and you don't necessarily have to write this down if you just pay attention, or you're welcome to write it down, it's up to you. So 5, would 5 be considered a whole number? Yes. Okay, an integer? Yes. And rational? Okay, 0.6, is it a whole number? No. Integer? 0.6? No. 0.6 would be, right? Would that be irrational or rational? It'd be rational. So yes, it's a rational number. No, it is not an integer. Okay, negative 2.3 repeating. Whole number? No. Can anything negative be a whole number? No. Integer? No. Rational? Yes, because it's repeating. Okay, negative 24, whole number? No, because the negative sign. Integer? Yes. And rational? Yes, it's also rational. If anything is yes in the integer category, it would also have to be yes in the rational category. Does that make sense? Like you couldn't put no in integer and say yes for rational. They have to go together. Okay, so what we're going to look at is we're going to tell whether each number is a whole number, an integer, or rational. Then we're going to graph the numbers on a number line and order the numbers from least to greatest. So really when you graph them on a number line, you're kind of already ordering them from least to greatest because you would have them in order on your number line. So if I were you, I would just use one of the lines on your notebook paper to make a number line. Doesn't have to be anything artistic or across your whole paper, but and we're going to go through and graph these. So first, if we look at 3, we're looking at 3 choices here. Whole number, integer, or rational. Is 3 which one of those? Or what combination of those? So 3 would be all of them, right? Whole number, integer, and rational. And then I'll graph 3. Okay, so the negative 1.2. Is it a whole number? No. Integer.
Yes.
No.
I disagree.
No, it has a decimal.
Has a decimal, so it can't be an integer, but it is rational. Okay, so now questions about how do I graph decimals. Some of you probably are good at this, but some struggle. I'm going to go, since it's negative 1.2, I have to go in between negative 1 and negative 2. And 0.2, think about it, what percent is that? Or what decimal? It is a decimal, but 20%. So I'm going to go 20% of the way. Or think about what is 0.2 as a fraction? 1/5. So I'm going to think of this, like my brain thinks of this little unit right here divided into 5, and I go 1/5 of the way, and I just estimate. And that's all you have to do, just the best you can. Okay, negative 2, whole number, yes or no? No, but it's integer and rational, and then I'm going to graph that. Okay, and then 0. Whole number? Yes. Integer and rational. Okay. So you do have portions of this on your homework where you have to like categorize what type of number it is and then putting them on a number line. So don't write this down, but just to review, opposites, think about it, are 2 numbers that are the same distance from 0 on a number line. So like 5 and negative 5 are opposite of each other, but they're both 5 steps away from 0 on a number line, right? So you will write this down though. Absolute value Okay, so absolute value is the distance between a number A and 0 on a number line. So the example I just gave you about 5, the absolute value of that would be 5 because it's 5 steps away from 0. This is the symbol for absolute value. It looks like 2 bars. So you would have like a bar, and then if I was using the number 5, then you put another absolute value bar. And that's the symbol we use for absolute value. If a number is positive, when you do the absolute value of it, it stays positive, okay? If a number is negative, then the absolute value of that number becomes positive. This is actually wrong. This should be a positive A. And then if A is 0, the absolute value of 0 is always 0. 0 doesn't change. So how I would say this if I were reading this out loud, I would just say absolute value of 5. That's how I would read that. Okay. So we're going to practice some of these. Okay, so these are all kind of jumbled together. I'll rewrite them. So for example, here's our first example. Absolute value of 2 would just stay 2, but you would remove the absolute value bars. Absolute value of negative 1.5. So this would become positive 1.5. Absolute value of 3.1 would be 3.1. And then absolute value of negative 5.7 would become positive 5.7. Okay, so the next thing is a conditional statement. This is also written as an if-then statement. And this is a statement that has a hypothesis and a conclusion. So this actually this crosses over into science class as well, because you work with a hypothesis and a conclusion and you make a statement, right? Like before you do an experiment, you would make a hypothesis, and this is essentially the same thing you do in science class. So it's saying that basically if this happens, then this would happen because of that.
Like if it's an integer, then it's also a rational number?
Yes. Or it can be about anything. It doesn't even have to be about math. So an example, like if it rains, then the soil will be wet, right? That's an if-then statement. If you are in 8th grade, then Mrs. Anthus is your math teacher. That would be an if-then statement. So a lot of times you have to pay attention to, does the statement fit with the hypothesis, and what conclusion, if it does fit with the hypothesis, what conclusion does that mean? And if-then statements are either true or false. I'm going to scroll this down. So they're either true or false statements. There's no like but or maybe or gray area. It's true or false. So if it's true, that means that the conclusion is always true when the hypothesis was satisfied, or if the hypothesis was correct. Okay, that means every time it's going to be true. If it was false, that means that you can find a counterexample. Okay, so a counterexample would show that the statement is false. So if you found one counterexample proving that it wasn't true, then the whole entire if-then statement would be not true. Okay, so I'm going to give you an if-then statement. If you are taking Algebra 1, then you are an 8th grader.
False.
I would consider that false because who else would take Algebra 1? Freshmen, right? So that's an example of an if-then statement. And then that was also a counter example. Well, no, that's false. Here's an example of something that's not true. Does that make sense?
So if it's false, you have to have a counter example?
If it asks for one, usually it does, yeah. But that was just kind of a non-math example of an if-then statement, and then we found a counter example to make it not true. Just like think about what we're all going through right now, right? In COVID-19. Here's an if-then statement. If you have COVID-19, then you have a fever. False, right? Does everybody have a fever with COVID? No, not everybody has a fever because there's so many different symptoms that people have. So that would be another example of a false statement because there are people that test positive that never have a fever at all. Okay, so now what you're really using this for is like with numbers, but those are just examples of non-math if-then statements. But it's not property. Okay, so now let's look at some math examples of if-then statements. So here's your hypothesis. A number, you don't really have to write these, just pay attention. A number is a rational number. So think about that. If I tell you a number is a rational number, then the number is an integer. So if a number is a rational number, then it is an integer. Is that true? Every time. Do you guys think that's true every time? I don't. So give me a counter example of a rational number that is not an integer.
Like 1.2.
1.2. So that's a good example. There's many examples, but 1.2. 1.2 would be a rational number, but you couldn't call it an integer because it has 0.2. Okay? Now, there are some numbers that make this true, right? But not every number makes this true. So if you find one that makes it false, that means that this is a false statement. Does that make sense? Like you just have to find one thing. Okay, so another one. Hypothesis. A number is, that should be A, not and. A number is a whole number. So if that happens, then the number is positive. So if a number is a whole number, then the number is positive. True? Always. I would agree with you. So you could come up with any example, right? Like 2, 5, 25. Okay. All right. So if the opposite of a number is positive, 1/2 of the number would be positive. If the opposite of a number is positive, 1/2 of the number is positive. So this one has a little tricky wording. So whenever I have something that kind of throws me off with the wording, I just think of a real number example. Like I put a number in there. So choose a number. 10. So if 10 is positive, or excuse me, if the opposite of 10 is positive, what's the opposite of 10? Negative 10. So does that work? Can I choose 10? No. So what number could I choose that has the opposite number positive? Negative 10. So if I choose negative 10, the opposite of that is positive 10, and 1/2. So here was my number. The opposite of that is 10. Okay, so 1/2 of the number is positive. So what is 1/2 of negative 10? Negative 5. So is that true? So 1/2 of negative 10 is negative 5. So this would be false because I just found a counter example. Everybody good with that? So sometimes when the wording is not as easy to follow, I just put a number in there. to figure it out. Okay. And I kind of go from there. All right. When you are graphing on a number line, I think some of your homework assignment has some greater than or less than. So we're going to add that on here. So if you see the words greater than, right, that shouldn't be new to you. Okay, so greater than or less than would be, this would be greater than. And that would, what does that little line under there mean? Do you know? Or equal to. So this is the two symbols for greater than. And we'll learn in algebra, sometimes we'll flip it the other way. It depends where the numbers are. Like when we're working with variables later. So then this would be less than, would be like this or like this. When you go to put these on a number line, let's say I'm trying to graph the number 5 and it's involving an inequality. This would be a solid circle. This would be an open circle. So if it has or equal to, you draw a solid circle. If it doesn't include or equal to, then you draw an open circle. And we'll look through your homework together. So your homework is a worksheet, 2.1B and 2.1A. And then let's pass that out.